Hello everyone, my name is Rojafari and I would like to welcome you to another video of data mining series. In the previous video, we did start our discussion about data reduction, and we specifically saw numerosity data reductions and what it is and the methods that we use to normally do numerosity data reduction. In this video, we're going to switch gear and move to dimensionality data reduction. First, we're going to understand what is dimensionality data reduction. After that, we're going to see two types of dimensionality data reduction. And in this video, we're going to see two methods. Of course, dimensionality data reduction is going to have multiple videos. So we're going to just cover some of that in this video. So let's get to the slides. Alright, so in this video, like I said, we're going to see what's the difference between dimensionality data reduction and numerosity data reduction first, and then we're going to see two types of dimension reduction. One is supervised, the other one is unsupervised. And in this video, we're going to focus on the supervised method. And specifically, we are going to see two methods that can be used as supervised dimension reduction, specifically regression and decision tree. Of course, there are going to be other supervised dimension reductions that you see sort of in gray here, random forest and brute force computational dimension reduction that we're going to talk about in the next video. So as we discussed, dimensionality reduction comes against the numerosity reduction. Numerosity data reduction was when we wanted to reduce the number of rows or our data objects. And as simple as that, dimensionality data reduction or dimension data reduction is basically reducing the number of attributes or columns in a data set. So that's where these two are different. We've got two types of dimensionality data reduction. We've got supervised and unsupervised. The simple distinction between them in your mind could be supervised dimension reductions normally come before the tasks of prediction or classification. These two tasks, if you remember from the videos that we did discuss them, are basically connecting the independent attributes to one dependent attribute. And, basically unsupervised dimension reduction is basically sort of finding out which are the independent attributes that are going to be more beneficial for the prediction or classification task. It comes against unsupervised dimension reduction, which is, more general purpose, and its goal is not to help a specific task. That's why it's called unsupervised. It's just to reduce the number of attributes and, reduce that number of attributes at the same time keep the most important part of the information in the data. So that's the difference between them. In this video, as I said, we're going to talk about two dimensionality data reduction that are supervised. The first one is linear regression. Linear regression was a prediction method itself. And here I'm going to show you how it can also be used as a dimension reduction method. You remember linear regression has a sort of like a universal equation that you use for creating a relationship with between your independent attributes and the dependent attribute. And in this example, we're going to focus on a data set example of using the historical stock market data to specifically be able to predict the next day Amazon stock market change percentage. So that's sort of the equation that we have. We've got Amazon stock market change percentage for the current day, and then we've got the change percentage for the previous day. PD stands for previous day, and we've got see, this is previous day, and then we've got previous week change percentage, which is for Amazon again. So this is previous week, right? And Dow Jones previous day change percentage. We've got Dow Jones previous week change percentage, and then we've got NASDAQ previous day change percentage, and also NASDAQ previous week change percentage. So we're going to see if we can use these independent attributes to predict this dependent attributes. And of course, this is our data. So this is our, these are our independent attributes or our predictors. This is our dependent attribute. Or our target. Right, so we use linear regression to find these relationship by these, estimating these betas. So when we calculate these betas, what we will get is going to be this. So this is the trained linear regression equation. So that's what basically we had already done before. We know we can sort of use this new equation that we found to basically use the previous day change percentage and these estimates, these beta estimates, to sort of have idea of what's going to be the change percentage for the next day. So this is what we've already seen from the linear regression. But now I'm going to tell you that linear regression actually comes with a lot more that has been developed, and we can use them. One of the things that linear regression gives us is the significance of each beta, or each estimated coefficient of the beta about each of the independent attributes. Basically, using that, basically a statistical test, it's going to tell us how significant that relationship between that the specific independent attribute is with the dependent attribute. Of course, what we see here, what you want to look for is this p greater than t, which is your p-value, right? So this is basically giving you the p-values of those tests. So the concept of p-value and what it is and how we can use it, it's kind of tricky, and everyone has sort of like a relationship with this p-value. They have an understanding for themselves. The easiest one is, if it's greater than 0.05, probably it's not significant. If it's lower than that, it is significant. So that might work for you, but once and for all, I would like to offer you a way to look at it, and it's going to work in every single situation when you have p-value. So p-value is something that comes with a statistical test, hypothesis test, and specifically about multivariate hypothesis test, the one that we have here. If there is a relationship between this independent attribute and this dependent attribute, every time the null hypothesis is going to be there is no relationship, there is nothing, right? So it's always going to be the non-existence of the pattern or relationship. So the null hypothesis here is that there is no relationship between this specific independent attribute and the dependent attribute. So the p-value is the probability of this null hypothesis being correct if this is the data that we get, right? So that means if the p-value, which is the probability value between 0 and 1, is large, it means that we suspect the null hypothesis probably is correct, right? And if the p-value is low, normally they say lower than 0.05, it's just a rule of thumb. If it's low, it sort of indicates that something else is going on in the reality, in the world, that the data that has come from this environment is not very probable based on our hypothesis. So basically, it sort of gives us a clue that it's possible that the null hypothesis is incorrect, right? So that's how you want to look at it. And when we look at the p-values for these attributes, we see that most of the p-values are rather large. You can see these are like 18%, 60%, and these are not p-values that sort of like would give us the sort of like heads up, hey, probably it's not. I mean, 13% is still a good probability for things to happen. But except for this one, which is around 5%. So using this logic, we can use these values and hypothesis test result to say, maybe I'm just better off keeping this one independent attribute, right? So now I use linear regression to find the best subset of the independent attributes to use for prediction, and that's what we mean by dimension reduction. So we move from this model, this linear equation, to this one, this much simpler one, because we saw in the previous one that the only one that had a rather low p-value, or like had some significance as far as it being able to have some relationship with the independent attribute. The dependent attribute was the Dow Jones previous state change percentage. So we switch our linear equation to this simpler one, and when we do that, now we get a new sort of like a coefficient, and also we see that when it's by itself, the p-value is 0. So it means that, of course, this independent attribute has a relationship with the dependent attribute. And if you pay attention to the adjusted R-square, when I switch between the previous linear regression and the new one, you see that the adjusted R-square improves, right? It improves from 0.04 to 0.5, which means that we have managed to improve our prediction, or like explaining this decision-making environment. So you saw we were able to use linear regression itself to do dimension reduction. So next, let's talk a little bit about the strength and the weaknesses of linear regression as a dimension reduction. Of course, the strength is statistical, it's well developed, well known, and it's very important. I mean, if it's a method is well known, it's an easier way to sell your result. I mean, everyone knows what's regression. There is a lot of research behind it, so it's much easier to say, okay, this result comes from a very well developed and well respected method. And it's also very straightforward. It tells you to either use an independent attribute or not to use the independent attribute. But the weaknesses is, linear regression only considers a linear relationship. So that's, maybe there might be some nonlinear relationship. Also, linear regression, even though you can include more attributes in the equation, but most of the time it only actually only consider the one-on-one relationship between the dependent attribute and independent attribute. And what we are looking for is the combination or interactions of some of the independent attributes with each other that would predict the dependent attribute, right? So that linear regression failed to consider that. And also, linear regression is only capable of doing this as a dimension reduction for prediction tasks. How about classification tasks? Of course, statistical methods are out there that can do similar things that linear regression can do for prediction tasks, such as discriminant analysis for classification with more than 2 classes, and logistic regression for classification of binary classification. So, just putting those out, discriminant analysis and logistic regression, at any point in time, if you felt like you need a statistical method to use for classification, discriminant analysis and logistic regressions, just throwing it out there. So let's move to the second method, decision tree. Decision tree, after you've spent a good amount of time tuning the decision tree, once the decision tree is tuned and you have a successful decision tree at connecting the independent attribute with the dependent attribute, the most successful one, then you can just look at it and see which attributes the decision tree is using for splitting the data and coming to a prediction. And you can see you get to the same value, Dow previous state change percentage. That's the only attribute we've used here. So here we can see decision tree also gets to the same result for this prediction problem. So now let's consider the differences between sort of the strength and the weaknesses of linear regression and this decision tree. So here we can see that some of the weaknesses of the linear regression has been dealt with, or it's kind of strength of the decision tree. So for example, we've got, do you remember we talked about how it only consider a linear relationship? Decision tree considers the interactions between the independent attributes as well. And so that's a strength considering it when we consider it with the linear regression. Also, do you remember we talked about how it only take into account the one-on-one interactions between them, so that's also taken into consideration, and also the nonlinear one. And we did also talk about how it's only capable of addressing prediction tasks, but decision tree can, as we discussed, address classification or prediction tasks. So decision tree can be used for dimension reduction. Of course, the other strength of decision tree is it's very visual and intuitive, but it's not without weaknesses. The first weakness is that the result of the dimension reduction is very specific to the algorithm, right? It's these dimensions or these independent attributes work well when you are using decision tree. There is no guarantee they're going to be working for other algorithms as well. So that's one thing you want to pay attention to. And then another thing is that the decision tree is just too visual. I mean, the weakness, the strength of it in one arena is the weakness in another way. It's being too visual makes it hard for us to see which attribute is really more important, which independent attribute is really more important than the other. Let me give you another example to sort of understand what I mean by this being too visual. So here we have another problem. Here we have a classification problem. The other one was a prediction. And what's the difference between classification and prediction? Is that our dependent attribute or our target is categorical, but the other one wasn't categorical, was the numerical. So that's the difference between them. Of course, these are our independent attributes, and this is our targets. So that's our data set, and we want to use the independent attributes such as the number of call failures, number of complaints from customers, and so on and so forth in a telecommunication company. We want to see if we can find patterns to be able to predict who's going to be churning or not. And churning means customers leaving us or getting the same services from our competition. So it's a sort of like a lost benefit from the customers if they churn, start using other companies' benefits. So that's the task here. And when we run a decision tree, tune it, and find the most successful decision tree, this is what it will look like. You will see, for example, the attribute, the independent attribute of status comes first, and then you've got complaints, subscription links, seconds of use, seconds of SMS or text messages, and so on and so forth. So now, after looking at this rather larger decision tree, now this last weakness that we discussed sort of like shows itself better. It's just too visual. How do we know which attribute is more important? I mean, is it just about the ones that are coming topper, the ones that are the router, sort of like divide the data first, for example, status and complaints, or is it about the number of times an attribute is shown on the tree? So this visual aspect of it doesn't really help us to have a ranking between these attributes. Not only that, we don't really know which one should we keep if we were going to use decision tree for a task of dimension reduction for other algorithms. And of course, in this example, we do also see that we can use decision tree for classification or prediction alike. Alright, so before finishing this video, let me offer some summary of this video. Of course, we talked about different things, dimension reduction, data reduction. We know what's dimension reduction. And we also talked about supervised and unsupervised dimension reduction. In this specific video, we talked about linear regression and decision tree as methods of dimension reduction, supervised dimension reduction as methods of supervised dimension reduction. And in the next video, we're going to discuss random forest and brute force computational dimension reduction as two other methods of dimension reduction, supervised dimension reduction. Until the next video.